So this time is the kinetics, and kinetics are very important for this chapter, and I wanted to give overall what does it mean kinetics, and we of course care about the reaction mechanisms of the d block metal complexes. So it's a coordination complexes, and we have to consider the rate of the reaction. How is the reaction? Is it inert? Is it stable? Is it fast, slow? What is the intermediate? Everything mechanism is very important. And if you, I remember when we came to approach some reactions, my supervisor at that time during my PhD asked about if you could do the reaction like in a matrix, isolated from the air. So we've been doing usually the reactions in the open air, and sometimes we needed not to involve any moisture. And the moisture is any gases, any water, especially the vapor water, can interact inside the reaction during the experiment, and could lead to impurity. Impurity was one of it's always challenge the researcher, scientific researcher, and how can avoid the impurity because once we do the reaction in just normal temperature, pressure, like atmosphere inside the lab, could the reaction be susceptible to any, or sensitive to any moisture, or could be present in the air, could be present with the solvent. I remember many times if the reaction or experiment is water, like moisturized, so we always start with a deionized solvent, or deionized water. There is a solvent, we have to dry the solvent as well. We had to take the solvent, and the solvent has some water with it. We need to dry it to make it pure. I remember especially dichloromethane was very good solvent to use for some nonpolar mixture. So we needed to use dichloromethane, or sometimes I remember ethanol or alcohol. And this alcohol, it was from the bottle, like from the provider or supplier, but we needed to dry it before we use it. So it's always better than to use, even if you use a dry solvent, you dry it from the water. When we say dry, what does it mean dry? You don't evaporate all the solvent, but dry it is you just take out or suck the water from it. So always anything in the nature can be mixed with water, mixed with moisture. So you need to isolate this water, because the reaction or the compound you are preparing could be bonded to a water molecule. And this bond of water molecule is unlikely for many compounds we need to isolate or purify. So from the beginning, before you do any reaction, you make sure you have dried samples or solids. You need to, some solids, I remember we put it under the dry agent, like in a in a room, glass covered, and should be no water or from the moisture from the air could react with the material or the chemical. So that's one. Second is the solvent should be dried. Remove water from it. Maybe you can do in isolation or matrix, we call it. Many times, now I just keep remembering 20 years ago what I have done during my reactions, how I end up with a disaster or with a good reaction. So most of my compounds, the prepared one, there was a water with it as a bridged water or the counter ion, no problem. But sometimes we had to isolate water. I didn't want the water to interfere with the bonding in the complex prepared. Or sometimes even when we prepare the sample, it's not always with crystallization. We had a problem how you crystallize the product where there is a water there as a counter ion or something. So it's very important to use dry solvent, dried products or reactants, isolate the reaction from the air, just not to have anything around you. And I remember when I was working in a fume hood covered, beside me there was another researcher, the other one, and there were always gas and in the lab, even when there is a ventilation in the laboratory, very nice ventilation, but many times any surrounding gases or something, they can interfere with the reaction. So, and give me a complicated procedure, and sometimes it takes months to have sample clean and pure. So again, sometimes we should, or we used to use normal temperature or freezing, just slow down the reaction, or make low rate of the reaction. So because some reactions are instant, they took maybe several seconds to finish. We have some reaction takes some long time to react. But with these, we wanted to introduce like reactants together in a slow motion, in very slow like method or status. So we needed to cool, use the ice from outside or liquid nitrogen just to slow down the reaction to make it slower and give me more product. So again, the reaction mechanism of the metal complexes were very important we are dealing with during our study. So we have kinetically labile or inert, dissociative, associative, interchange. So activation parameter, these all and substitution in square planar and octahedral. Electron transfer as well, very important to do the reaction mechanism of d block complexes. So we need to deal with these things. So kinetic and thermodynamic stability, two types of stability. Kinetic, which is labile or inert. Labile is very fast, inert slow. And we need to consider the stability constant, K. And then thermodynamic stability involves metal ligands, bond energy, concerned with several parameters such as heat formation, delta H, endothermic, exothermic, change in the entropy delta S, how many steps needed, Gibbs free enthalpy delta G, initial and final stage. So these are the two types, the kinetic and thermodynamic. They are very important to do when we deal with the coordination chemistry. So complexation reaction, how to form the complex. So there is a metal and ligand to make a metal. This is formation of metal ligand or complex, or deformation, dissociation, comes back to the ligand separated from the metal. So the reaction takes place in stepwise fashion. The reaction above is often followed by additional reactions, such as Ml plus L to give you Ml2. So there is like a second step. First, the metal reacts with one ligand, then with a second ligand, and so on with the third ligand. So it's a stepwise. But the total reaction will be Ml n minus 1 plus L equal to the MLN. So this is, at the end, we have several steps to reach to the final one. Monodentate ligands usually added in a series of steps. Monodentate ligands. So we added dropwise like. With polydentate ligands, the maximum coordination number of the cation may be satisfied with only one or a few added ligands. Equilibrium constant for complex formation reaction. If we check this, let's have a look. Let's check the equilibrium. And now you can see to the right side concentration. So K, the K constant equals the concentration of a product divided by the multiplication of the reactants concentration. And generally written as the formation constants. So the K is the formation constant, which is, if you take this equation, metal plus 2 ligands to give you Ml2. So you are dealing with concentration of metal and concentration of ligand, twice of the ligand. So you end up with one concentration of the product, Ml2. So what's this? Now, beta 2 is the final, will be concentration of Ml2, the product, divided by concentration of M times L to the power 2, because we have two ligands, so you make it to the power 2. So what's this? You have it equals to K1 times K2. So how has that happened? Metal plus 3 ligands will give you Ml3. So again, you can see we have, okay, when we dealt with, you remember now I show you, when you deal with Ml with 2 ligands, it means you have 2 Ks. The M reacted with 1 ligand, so that's K1. And there is M reacted with 2 ligands, this is K2. So if you make them together, you say the total B2 equals the concentration of Ml2, the product, divided by metal concentration times ligand to the power 2. And this came from K1, K2. Whereas if you use the three ligands, with the metal, you end up with ML3. What will happen? The B3, here we call it B3, concentration of ML3, the product, divided by M times L power 3. This came from 3 types of K, K1, K2, K3. So the overall formation constants are product of the products, stepwise formation constant for the individual steps leading to the product. And this is it, M plus how many L ligands to end up with MLN. And this is the final Bn is the concentration of mLn divided by concentration of metal times L to the power n. And this comes from K1, K2, up to how many Ks you are doing. So a general relationship is overall formation constant. This is the beta. It's the overall formation constant, which is K1, K2, K3, so on. And we have this equation about Ki. So Ki is called stepwise formation constant. So the K1, K2, K3, up to K. So all of these, they are Ki. And this is a Ki called stepwise formation constant or stability constant. So with only few exceptions, there's general slow descending progression in the values of the Ki's in any particular system. So this is illustrated by the data for the cadmium-2 NH3. When you connect cadmium-2 to the NH3 system where the ligands are uncharged, NH3 is neutral, and the cadmium-CN system, the ligand are charged with minus charge. If you see here, stepwise stability constant, cadmium-2 plus NH3, what we will do, it's a cadmium and NH3 to the power 2. Now, this is one NH3, one ligand, and the K constant is 10 to the power 2.65. Whereas when you introduce another NH3, you will end up with cadmium NH3 by 2, oxidation number 2. Cadmium here, the second ligand added, the K constant would be 10 to the power 2. You add more NH3, you end up with 10 to the K to the 10 to the power 1.4. Another. So you can see the rate of the reaction, the K constant is reducing every time you add one ligand. So what is the total overall formation constant before? Because 4 times, it's, you put them together, will be 10 to the power 712. So 712 came from 2.6 plus 2 plus 1 plus 0.93. All of them will be 7 to the power 12. So this is the total formation constant. So principal reasons for the decrease of Ki. Why the Ki being decreases? Because statistical. Second, the charge of the metal that will affect the decrease in the K constant, right? So charge of on the metal, the higher charge increases steps with negative ligands. The statistical, countable, and steric effect. Steric effect, each atom within a molecule occupies a certain amount of space ready for electrophilic reaction, prevent SN2 reaction. So steric effect, in which direction the ligand is coming, that will affect the K. So cadmium-2 plus Cn, let's come to the minus charged, will be cadmium Cn plus, and the K constant will be 5 to the power 48. Sorry, 10 to the power 5.5. And then you add another Cn minus, another Cn, another Cn, you end up with the total overall constants would be 4, and you add everything together will be 10 to the power 18.8. So look, this is in the case of the minus ligand or an ion. So as ligand is added to the solution of metal ion, Ml first forms more rapidly than any other. Yeah, you can see the first ligand added, the faster the reaction. K. What does it mean? It means the formation of the product is bigger than the reactant. So the reactants are reduced or decreased because they combine together and they give bigger in the first step. So first step is very important. If you introduce one ligand, this is the fastest step. When you add another ligand, will be less fast. When you add the final ligand, will be the slowest step. So as addition of ligand is continued, the ML2 concentration rises rapidly, while ML concentration drops. Then ML3 becomes dominant, ML and ML2 becoming unimportant, and so forth. Now, types of substitution mechanisms. You can see H2B suggested that those complexes in which ligand substitution occur within about 1 minute, look, the speed of reaction, 1 minute at normal room temperature, considered labile. So now, if the speed of the reaction was less than 1 minute, this is labile. So how can we say this reaction is fast? And how can we say it is inert? So labile or inert, fast or slow. If it was less than 1 minute, the reaction took place, finished, room temperature, it will be labile. More than that will be inert. There is a difference between thermodynamic, stable and unstable, with kinetic term, labile and inert. So the thermodynamic, you have stable, unstable, but the kinetic, you deal with the labile and inert reaction. It's also possible to predict the rate behavior of complexes by considering the charge and size of their central atom of the metal. Stability and lability relationship. Small, highly charged ions form the most stable complexes. Small, highly charged ions form the most stable complexes. These ions form complexes that react slowly. There is a decrease in lability with increasing charge of the central atom for the isoelectronic series. So we can see here, there is a decrease in lability in the speed of the reaction. Decrease. So when you have SF6 less than PF6 less than silicon F6 less than aluminum F6. So what do we have here? We have aluminum oxidation to the left is +3, silicon +4, phosphine +6, sulfate +6. So what is it now? So the less charge will be more active or labile. A rate of water exchange decrease when increase cationic charge in the order. Now we have a water coordinated, but what do we have here? We have the rate of water exchange decrease with an increasing cationic charge. With a decreasing cationic charge. Okay, from the left, sodium, we have sodium 1, +1. Magnesium in the middle, +2. And aluminum is +3. So less charge, more labile. Complexes having central atoms with larger ionic radii react faster than those having smaller central ions, for example. So larger ionic radii, larger. You have strontium calcium, magnesium. In this case, similar charge, but the ion reacts faster when it will be bigger central ions. Series of octahedral metal complexes containing the same ligands, complexes having central metal ions with the largest charge to radius ratio will react slowest. This rule of charge to radius ratio cannot be applied on coordination number 4 tetrahedral and square planar. So these are applied only for octahedral because they have different reaction mechanism. For square planar complex, it is not possible to apply successfully charge to radius ratio as in the following. So there is no way to, these are square planars. As the size of the metal ion to increase, the rate reaction decrease. Rate of the reaction decrease. The rate of chlorine exchange by orate Cl4 minus approximately 10 to the power 4 times faster than those with the platinum minus 2. Platinum plus 2 oxidation number here with the PT Cl4 minus 2 is platinum here plus 2, whereas a platinum here plus a 3. So orate chloride 4 minus is oxidation will be a 3. So it will be faster by 10,000 times than the reaction in PtCl4 minus 2. So this is very important. So to see which one is faster in the reaction. The rate of reaction depends upon the mechanism, activation energy, breaking metal ligand bonds, everything. Kinetic thermodynamic stability coordination compounds. Here we discuss mechanism of ligand substitution and electron transfer reactions in coordination complex concerning square planar, tetrahedral, octahedral, for which kinetic data is plentiful. Okay, so ligand substitution generally, what do you have? ML and X with Y. So the Y will replace the X, and then it will become ML and Y, and the X will be out. So X is leaving group and Y is entering group. Kinetically labile and inert complexes. So metal complexes that undergo reaction with T or half time less or equal to 1 minute are labile, fast, unstable. The sample here is iron 3, 6 aqua, high spin, D5 undergo rapid substitution. If the reaction takes longer than 1 minute, it's called inert, kinetically inert or slow. And for example, you have here chromium 6, aqua chromium 3 goes slow substitution. Types of kinetic substitution mechanism. We have dissociative, D. This is types of kinetic. So you remember there are 2 laws of kinetic, SN1, SN2. So SN1 is a dissociative reaction, correspond to substitution reaction for first order kinetic. So intermediate compound is a lower coordination number than starting complex. ML and X will give away the X, so bond breaks, and there will be an intermediate. So that's the starter. Okay, so just let me do this. Here we have starter. The starter is MLNX. So forming the intermediate, okay, plus X. X has left. Now, Y will come as entering group. X will be leaving group. So how can Y replace X? First, there will be intermediate of X left, and then Y will be introduced to join or linked with MLN with the intermediate, and to get the product, final product will be MLN Y. So this is, we call it the lower coordination number. It's a dissociative reaction. Whereas the associative A, the intermediate has a higher coordination number. So here, if you see, the intermediate is only MLN, whereas here is MLNX, then plus Y, enter the group. Sorry, again, similar thing. When you start with MLNX and plus Y, this will be a higher coordination number, will give you MLNXY. This is the, you can see, this will be the intermediate. Whereas here, you can see this is the intermediate. This only MLN intermediate. Here, no, they join together in the associative. Associative, you join the Y with the entering group with the present of the leaving group to do one intermediate, then the leaving group will leave the X and remaining the Y there. So you can see here is the leaving group at the final step. So N is the number of ligands involved in both cases. Both dissociative and associative have two steps pathways and intermediate, but the intermediate here is different. Okay, you see, this is a crowded intermediate in the A, whereas here will be less coordination in the intermediate of D. So an intermediate occurs at a minimum energy. It can be detected and isolated, but transition state cannot be detected or isolated as occurs at maximum energy. When there is a slow step, you can detect a minimum energy. Metal complex substitution pathways, bond formation between metal and entering group, named interchange mechanism. So there is an interchange mechanism, I, correspond to second order kinetic SN2. So now SN2 is what? SN2 is coming MLNX plus Y. The Y will bond to the metal to the left side, and the X will remain like joined or linked. So to give you then leaving the X and remaining the product MLNY. So this is second order kinetic. There is transition state, but in the SN1, there is intermediate. Here is intermediate state, whereas here there is a transition state. Transition. So interchange mechanism has no intermediate but transition state at higher energy. Reaction rate depends on the starter and entering group. Concentrations involved in increase in coordination number, SN2. Indicates two types of mechanism. Same thing, dissociative ID and associative interchange IA. So here, the bond breaking is dominance over the bond formation, whereas the associative is bond formation dominance over the bond breaking. So reaction rates in IA mechanism is dependent on the entering group, but reaction rate for the ID shows a small dependence for entering group. Okay, wait. So here what we have the reactants here. Gibbs energy increase. We reach to the transition state. And this is the delta G between here and there. Comes back to the intermediate, the slow step. Then we go up less than this one transition state. The difference in the Gibbs reaction will be less. And then from the transition state to the product, you have the lower energy. You go with higher energy, down, little higher, less energy. Substitution reaction, MLN plus L. It will be MLN, N minus 1, L plus L. So the label complex is fast. Substitution reaction in a few minutes. Whereas the inner complexes, slow substitution, more than an hour, kinetic concept. So not to be confused with the level and unstable thermodynamic concept, delta G is less than 0. So we come to the transition metals with D3, low spin, D3 and low spin D468 found to be inert. D8, high spin is intermediate, whereas the label one, the fast one, you have the D1, D2, low spin, D4, 6, 7, and 10. These will be labeled or fastest when they are low spin. In the low spin, here we have inert low spin. Both cases we have which one is inert, which ones will be labeled. Mechanisms of ligand exchange reaction in octahedral complexes. You can see here MLNX plus Y will give you MLNY plus X. So entering group, leaving group. This will be dissociative and this will be associative. And every time we have MLN and here we have the transition MLNXY. So interchange, no, the transition it will be in the interchange. Okay. Classification, you have here our substitution mechanism. We have the associative 7 coordinate transition states, octahedral, or dissociative. We have 5 coordinate transition states. And each one of them, which one is having dissociative D, associative A, and in the middle will be I, interchange, dissociate or interchange associate. Alternative levels, SN1, limiting first order, SN2, limiting second order. Principal mechanism for ligand exchange in octahedral complexes. This is what's happening. The ML5X will go K1 constant. It's slow to give you the ML5 leaving group. When you add plus Y to the intermediate, you can end up with K2 second K fast to give you the product. And the rate here depends on the K1 times the concentration of ML5X. Whereas here, associative, you have the ML5X plus Y, they stays together to be associative, then X will leave. This is in K1, slow. When the X left, quickly will give you with K2 ML5 Y. And here you can see the reaction rate depends on the K1, the product, and multiply by the concentration of Y. Okay. And here you can see the free energy and how we have dissociative 5 coordinated intermediate, most common, 5 coordinate. But here, once you have the 7 coordinate will be associative all together. Here, part of them. So mx plus y will link the y together and then give you my plus x. Whereas here, mx plus y will give you mxy, and then x will leave, will give you my plus x. They are the same product, but in different intermediate. Experimental evidence for dissociative mechanism, right? We can, it's been checked for ligand with this nickel 6 water. So the ligand will substitute the water, okay, 1 water. So being kicked out and the ligand coordinated to the nickel. There's a K here. So with the fluorine, if the ligand were a fluorine, so the rate of K per second is 8 times 10 to the power 3. And the log K will be 3.9. Whereas if you use thiocyanate, will be less. If you go with carboxylate, will be more. If you go with ammonia, will be very less K. And the water, if you do the water, will be the bigger K. Okay, so rate is independent of the nature of the ligand. The rate is independent, not depend on the nature of the ligand. Experimental evidence for dissociative, we have here the slowest rate reaction. You come from the lower to the here, slowest. So we go increase. Okay. So you increase from lower to the upper. K is being measured. And this always experimental. These are experimental. So just we want to show the weakest metal ligand bonds, and then you increase to the strongest metal ligand bond. You can see how much you decrease the K. Decrease. What does it mean, K decrease? You are dealing with, I remember when I say decrease K, you are talking about concentration of the product divided by multiplication of the concentration of the reactants. So when K is increased, it means the product more concentration. When the K decreased, it means what? It means the lower is increased. The reactant concentration is decreased. Inert and labile complexes, some common ones, exothermic, favored large K. So exothermic. You have here large EA slow reaction. We have here, look at the curve. You have higher energy, but here we have slower when it is endothermic. So the energy is less for the endothermic reaction. Endothermic, so they absorb energy. Exothermic, they produce energy. Lebanon or inert. So ligand field activation energy equals in the pyramidal is less than or minus octahedral. So this is the octahedral. Energy is up, give you the 5 coordinate, and then you return to the octahedral 6 coordinate, and the delta G here is different. Why are some configuration inert and some are level? Why? So crystal field stabilization energy as well involved. So we have here low spin, strong field. So this will be inert when there is low spin, strong field, inert. Where here you have crystal fields in units of delta for octahedral square pyramidal SP, shown followed by the change in crystal field stabilization energy, process ML6 octahedral to ML5 square pyramidal. A indicates a gain of more crystal field during the process, and A indicates a loss in CFSE. Substitution in square planar. What's happening with the square planar? So they prefer SN2 reaction. What does it mean? It means mechanism by formation of 5 coordinate number with additional ligands. So ML4 plus X will give you ML4X. Then it will release the L, and the X will replace one of the L's of the ligands. So due to large space around the metal and no steric effect, you can see X entering. So it was square planar, now became what? Square pyramidal. Here is 4 coordinate, here is 5 coordinates. The 5 coordinates will lose 1 to return to the square planar. Square planar complexes, the trans effect we have here, if there is 2 ligands, T and X, so plus X minus Y. So leaving X or adding X and leaving Y. So the ability of the T to levelize X. So now what's the difference? So be leaving X and they are replaced by Y. So here you have spectral ligand series of the cobalt carbonyl equals to Cn, but here the olefin bigger than B earth and so on. So these been measured experimentally and found which one in the square planar have a trans effect. Synthetic application for trans effect is here. So you have 4 amino groups with platinum. You introduce 1 chlorine, replace 1 amino group. Adding another chlorine will give you trans molecule. Whereas if you have 4 chlorine, you add NH3, replace 1 chlorine, another NH3 will give you cis. So here, how can you prepare specific geometry? Is it you end up with cis or the trans? Which product you start with? That's important. If you start with tetrachloroplatin and you want to prepare cis or trans, you end up with cis chloro platin or cisplatin. If you start with platin with NH3 by 4, you introduce chlorine every time, you end up with trans platin. Look how is important. Which product you start with is important. Which one you introduce for adding group. So you have to have the or entering group. Now you can control the reaction. And here other examples. You have 2-pyridine, 2NH3. You introduce chlorine, 1 twice. Replace the pyridine. So you end up with what? Trans platin. But if you what's this trans again? If you go with cis pyridine, and this is, you start with the transpyridine. Cispyridine, you give chlorine once and twice, you end up with trans chloro, and so on for other reactions. So mechanism of ligand exchange reaction in square planar, you can see here, you always, if you lose X, you enter it, you add S, you can see these. In this reaction, you add Y. So 3 ligands, 3L, the X will stay, the Y will enter. So again, every reaction is being measured and depend on the concentration. Substitution reaction square planar ML4. So this is the case of D8 configuration, usually for square planars. Most of this D8 or all of them, they form square planar. In a crystal field of kinetic work on square planar system being carried out on platin-2 complexes, which are important in the medical uses, for medically, for anti-tumor. So rate equation, mechanism and trans effect for square planar. So experimental work on square planar PT2 complexes associative mechanism SN2. Displacement, that means substitution of chlorine by water in platin Cl4 minus 2, indicating bond formation. So you have the starter here, you have entering group, so they come in different direction as a transition state. This is SN2. And then product is being made, and leaving group is the chlorine. Kinetic trans effect, kinetic trans effect. If you see here, we have the platin with 4 coordinates. So the Y group attacks from above, square planar, this is the square planar, or is coming attack from below of the square planar. So in which way? That's being studied as well. So the choice of leaving group in square planar complex determined by the nature of the ligand it runs to it. In the majority of reactions, substitution of square planar platinum-2 stereospecific, we call it steric effect. The entering group takes the coordination site previously occupied by the leaving group. So if you have this square planar and you introduce the nucleophile, so this will enter platin, the Y, X will stay, Y will enter. Leaving X, the Y will be replaced or substitute the X. So attack by entering group at the square planar center, the nucleophile Y coordinates to give trigonal bipyramidal, and then after that losing the ligand X to reform square planar. Trans effect, certain ligand cause a group opposite to them in transposition in square planar to replace easy, or the effect of coordinated group T upon this rate substitution reaction of the ligands opposite to it. Ligand which has certain ability is said to have strong trans effect. Again, NO2 bigger than methyl group, bigger than halogen, bigger than pyridine, ammonia, or so pyridine with ammonia is the similar and bigger than water. So everything trans effect is important to choose which ligand we're gonna prepare. So reaction of cis and trans platinum diamine dichloroplatinum trans are prepared by different substitution routes. As I said, you start with which one to end up with which desired geometry. If you want to end up with cisplatin, you start with tetrachloroplatine, and amino group will come enter. Okay, and then cisplatin will produced. If you start with 4 amino group, you end up with a trans platin. Okay, and this is the mechanism. In general order, trans effectability of ligands for direct trans substitution span factor of about 10 to the power 6 in rate. So again, this is the series. Which one is bigger? You can see the double bond equals to the cyanide, equals to the carbonyl triple bond, bigger than hydrogen, methyl, phenyl, and so on. So the trans effect influence is useful for devising synthesis platinum 2 complexes. So as we said before, what can you do? If you want to prepare trans NO2 dichloroamine, you have to start with tetrachloroplatinum and introduce NO2 first. And NO2 will bond, leaving Cl, then NH3 you add to end up with trans chloro, NO2 NH3. Whereas if you start with tetrachloro, give amine, and then NO2, you will end up with cis dichloro. You see? Do you want cis or trans? You have to introduce or give which group entering group first. Which one first will give you different product. So mechanism in biology, cisplatin is very important. So this is what we said in medicine using the cisplatin anti-tumor. So medicine, how can be administered to the patients. It will be giving as a aqueous saline solution. Half of platinum binds in a serum proteins. Excreted, isolated, the rest of the distributed among various tissues. Blood plasma, the drug remains largely cisplatin. So they are to high chloride ion concentration of about 0.1 molar. the neutral molecule cisplatin diffuses passively across the cell membranes into the cytoplasm, where it encounters a lower chloride concentration, is about 3 micromole. Hydrolysis produces cationic complexes such as cis, water inside, Cl, NH3 by 2, that diffuse to DNA or of the tumor itself, a poly, an ion, where then bind to form cytotoxic lesion or harming the tumor. The hydrolysis reaction of cisplatin is an important aspect in biological activity. Chloride ions are displaced in a stepwise manner to form aqua and hydroxo species. Hydrolyzed react rapidly with the DNA of the tumor. Tumor cells than neutral cisplatin does. What is important here is by changing its chemical form by transforming from neutral molecule to a cation, the drug becomes trapped within the cells, where it is able to damage the genomes by binding to the DNA and exhibit anti-tumor activity. Little toxic side effect of the drug is present on formation of cisplatin. DNA adducts. Now I show you. This is the cisplatin anti-cancer drug. Contain 2 chloride cis, 2 amino group cis. Intervene IV. Okay, it goes to the bloodstream. Still, we have it as cisplatin. Then entering the cell membrane, and then we can see starting diffusion. So in this case, it will take water from the plasma, cytoplasm, and leaving 1 chloride. So this water either enter the platin, or another water will replace another chloride, or we can see deprotonate of one of the water to give this product, OH. So entering the cisplatin to the cytoplasm, what will happen? We will replace, it will replace the 2 chloride ions by 2 waters, and even one of the water will be dehydrolyzed to stay as hydroxide. So now we have 3 types of platin compounds, very active. They are attacking or bond to the DNA of the tumor and kill it. Okay, so they bind in these forms, you see, these kind of forms, they are active to treat or to bond to the DNA of the tumor. But when it is a cisplatin, they do nothing. So this reaction is going take place inside the cytoplasm, and they produce 3 different. So this type of cisplatin cannot bond to the DNA unless replace the chloride with water molecule, and one of them will be hydroxide, very active, can bond to the DNA and kill the cancer. So there is another case of electron transfer, redox reaction. We have M1Ln plus M2Ln will give you M1Ln. This is adding 1 electron. So Okay. And here, losing one electron. So when this X plus 1, it means oxidized. When this is gained electron, this is reduced. So the very fast reactions, much faster than ligand exchange, may involve ligand exchange or not. Very important biological process. Metalloenzymes always involved electron transfer for activation. Outer sphere mechanism, we have cyano. Okay, here is ferrate 4, ferrate 2, hexacyanoferrate 2 ion plus iridium iridate, hexachloroiridate 4 ion. So that will give you the 6-cyano iron -3 and iridium Cl -3. So you are changing the outer sphere oxidation number. Here were -4, -2. Here became -3, -3. If you come with +2, +2, you end up with a +1, +4. So now we are exchanging the oxidation from outer sphere. Reaction 100 times faster than ligand exchange. Coordination spheres remain the same. If you see a tunneling mechanism, we call it A and B. Take energy and solvent cage with A and B, and then separate A plus B. There is a delta G change. Inner sphere, if you introduce this complex with this, +2, +2, you can bond together, but then the cobalt, chrome, these 4 will become cobalt 3, chromium 2. And then together they will lose, or they bridge the chloride together. Then they leave each other as a cobalt 2, water 5 NH3. So this is octahedral, and the chromate would be 3. And then you have octahedral as well. So what's the result of this reaction? You end up with cobalt H2O6 plus 5 ammonium. Inner sphere, oxalate X plus red, K1, end up with oxalate X red, K3, leading to oxalate water plus redox, or red X. If you come back, you are using the K4, K2, and K4. Reaction much faster than outer sphere. Electron transfer, bridging ligand often exchanged. And we have, this is a different approach of doing the inner sphere mechanism.